Namaste and warm welcome to the lecture on mathematical foundations for machine learning. We were looking at the idea of orthogonality and we were looking at what we call the orthogonal complement, vector subspaces and so on. Now, what we want to do is we want to go a bit further in the sense like I want to look at can we have a set of vectors orthogonal, or can we pick up certain can we pick up a set of vectors which are orthogonal to each other in a vector space, and if we are able to pick up, what is the advantage that we have in picking up these orthogonal vectors from a vector space. Say for example, I have a vector space, n dimensional vector space, say Rn I pick n orthogonal vectors from this vector space Rn, right, n orthogonal vectors from this vector space Rn. So, the question that I am going to ask is, will these n orthogonal vectors help me with something, right, help me with something in the sense, yeah, can I have say for example, I had linearly independent vectors, like I had linearly independent vectors for a vector space to be the basis for that particular vector space. Suppose I take an n dimensional vector space, I have n linearly independent vectors. I said look, these n linearly independent vectors would turn out to be the basis for that particular vector space, one of the bases for the particular vector space. Now we want to slightly move away from this linearly independent set, but I want to look at even a very interesting idea of orthogonal set. I want to look at an orthogonal set and then I ask a question, can I have a set of orthogonal vectors to be a basis for a vector space? In turn, what I am asking is, if I pick orthogonal vectors from a vector space, will they be linearly independent? If they are linearly independent, which we really do not know, in case if they are linearly independent, the question that we ask is, how do we express every vector in a vector space as a linear combination of these orthogonal vectors? Would it be as computation intensive as what we used to do? For example, you have a set of linearly independent vectors, you want to find out the representation, or you want to express another vector in terms of the set of linearly independent vectors, you have to put that in the matrix form and then you have to do the row reduced echelon form to get the coefficients and then say this is what it is. Quite a laborious task. Suppose if I take n orthogonal vectors from an n dimensional vector space. So, the first question that we asked is, would these guys be a basis for that vector space? Number 2, if they turn out to be the basis for the vector space, would they help me in getting my coefficients in a less what would you call, in a less computation intensive manner rather than doing all this row reduced echelon form and stuff. And if I get this, what other advantages do I have? Have I seen this somewhere else, this orthogonal fellows and stuff? So, have I seen this somewhere? So, these are the questions that we are going to answer in this particular lecture, right. So, I am going to look at orthogonal vectors. So, that will be the focus of this lecture, orthogonal vectors, and then towards, I mean, we will move to orthonormal vectors from here and see what happens. Okay. So, we say that a set of vectors let us say u1, u2 etc. un is said to be orthogonal set if ui dot uj is equal to 0 for I not equal to j, right. So, I am going to claim, I am going to say that look, I am going to define set of orthogonal vectors as set of vectors where in which the dot product of the vector with any other vector is going to be 0 if I is not equal, I mean that is why we said it is any other vector, right. Okay, this is what I have, and I am going to make another definition here. I am going to include one more, a set of vectors let us say V1 V2 Vn, V1 V2 Vn is said to be orthonormal, is said to be orthonormal if Vi dot Vj is equal to 0 for I not equal to j and is equal to 1 for I is equal to j. Now, what do we mean by this orthonormal set? It says first the vectors are orthogonal to each other, that means the dot product with a vector with another vector is 0, that is the condition which is expressed here, the first one where it says Vi dot Vj is 0 if I is not equal to j. And the second line says something interesting, it says if I is equal to j we are going to get Vi dot Vi, right. And it says Vi dot Vi is 1. Now, what is Vi dot Vi? This is basically the length of the vector, this is basically the length of the vector Vi, and it says the magnitude of that vector is basically 1. That means I am going to say that each of these vectors that I have V1 to Vn, they are going to be of unit length. That means a set of vectors is said to be orthonormal if they are pairwise orthogonal to each other and they are unit vectors. That is the definition of orthonormal set, exactly an orthonormal set of vectors. Now, the question is, okay, so what, we have orthogonal vectors, we have orthonormal vectors. So, the question, so what is that we are going to get? Now, I am a bit curious here to figure out, I will take orthonormal vectors V1 to Vn and I want to ask, is this set V1 to Vn which contains this orthonormal set V1 to Vn, V1 etc. Vn, is this set linearly independent? Because if they are linearly independent, I have an advantage, the linearly independent vectors would actually become a basis for that particular vector space. So, the question that I ask is, are the vectors orthonormal vectors? V1, V2 etc. Vn linearly independent. That is a worthy question to ask. So, what is it to say linearly independent? We know the definition of linearly independent, nothing great about it. We say that for linear independent, for V1, V2, Vn to be linearly independent, we must have C1 V1 plus C2 V2 plus etc. plus Cn Vn is equal to the 0 vector implies C1 is equal to C2 is equal to etc. Cn to be equal to 0 for real scalar C1 Cn. For real scalar C1 to Cn, we want to check whether that happens. So, what we have? We have this. So, I want to look at let C1, C2 etc. Cn be real scalars then we want to look at the linear combination which will give me the 0 vector. We want to look at the linear combination of V1, V2, Vn that would give the 0 vector. that gives the 0 vector. So, what are we going to do? I am going to look at this 0 vector is equal to C1 V1 plus C2 V2 etc. plus Cn Vn. We have already defined the nature of V1 V2 Vn. This is basically the set of orthonormal vectors. So, we have already claimed this orthonormal vectors. The question that we ask is, are they linearly independent? We are just going towards that. Now, I really do not know if they are orthogonal I mean they are linearly independent or not. So, what do I do now? Let me do the simple stuff. So, what I will do is I will take V1 dot product, I will take the dot product of V1 of this on either side I take the dot product with V1. So, I have V1 dot 0 is equal to V1 dot C1 V1 plus C2 V2 plus etc. plus Cn Vn, which is nothing but the left hand side becomes 0 vector 0, it is a scalar 0, right. V1 dot 0 is basically the scalar 0. So, what do I get? I get V1 dot C1 V1 plus V2 dot C2 V2 plus etc. plus V1 sorry this is V1 dot C2 V2. So, I have V1 dot Cn Vn, which is the same as C1 into V1 dot V1 plus C2 into V1 dot V2 plus etc. plus Cn into V1 dot Vn. Now, by the definition of orthogonality, these guys will get knocked off, and we know that V1 dot V1 is equal to 1, every other fellow will get knocked off. So, which implies 0 is equal to C1 into 1, which implies C1 is equal to 0. Now, what you do? You take the dot product of this entire expression with V2, you will see that C2 is 0. You take the dot product with C3, I mean V3, you take C3 is equal to 0, you will get. You take with Vn, dot product with Vn, you get Cn is equal to 0. That means the scalars is 0. Is this clear? So, this implies by taking dot product with each of those vectors V1 to Vn or V2 to Vn, dot product of each of dot product, let me call this as expression 1, dot product with V1 to Vn in 1, we see that C1 C2 Cn must be 0 for 0 vector to be equal to C1 V1 plus C2 V2 plus etc. plus Cn Vn. Therefore, this implies V1 V2 etc. Vn are linearly independent. Right, they are linearly independent. Therefore, what do we say? Every set of orthonormal vector is a linearly independent set. Oh, that is interesting. When I say every set of orthonormal vectors is a linearly independent set, now I can use them as basis. Therefore, what we are going to do is every set of orthonormal vectors will be a basis for a subspace or vector space, subspace or a vector space. Okay. So, now comes the question, now suppose if I have orthonormal vectors, how do I get the, how do I express every vector in that vector space as a linear combination of this orthonormal vectors, or in turn what I ask is how do I express, or what is the basis expansion in terms of this orthonormal basis for a given vector in that vector space. So, this set of vectors we are going to give a name for this. So, the set, this basis whatever we have written here, orthonormal vectors, this basis of orthonormal vectors is called an orthonormal basis. Is called as an orthonormal basis. So, the question is, given V1, V2 etc. Vn an orthonormal basis for an n dimensional vector space V, for an n dimensional vector space V, and a vector let us say B in V, what is the basis expansion of V what is the basis expansion of B in terms of the orthonormal basis. V1, V2 etc. Vn. So, what do I want? I want to express this B vector as let us say alpha 1 V1 plus alpha 2 V2 plus etc. plus alpha n Vn, where alpha i's are all real, I is equal to 1 to n. So, how do I get this coefficients alpha 1, alpha 2, alpha n? See, if we were to do it with a linearly independent set of vectors. So, here okay, we are going to say there is n dimensional vector space, therefore, each of these vectors V1, V2 are going to have n components. So, V1 will be let us say V1 1, V2 1 etc. Vn 1, and we are going to have Vn to be Vn 1 etc. I mean V1 n etc. Vn n. This is what we are going to have. Now, the question is how do I get the coefficients alpha 1, alpha 2, alpha n? There is absolutely no problem here, it is pretty simple and straightforward. We will do the same magic what we did for getting the 0 vector as a linear as a linear combination of these orthonormal vectors. So, what we do is we do the same thing. Let us take up this, what are we going to do? We are going to say that look, take V1 dot B. What is V1 dot B? V1 dot B is basically V1 dot alpha 1 V1 plus etc. plus alpha n Vn. By the definition, we have this V1 dot alpha V1 plus V1 dot alpha 2 alpha 1 V1, V1 dot alpha 2 V2 plus etc. plus V1 dot alpha n Vn. By the definition of orthogonality, these guys are gone, this will be just alpha 1 because V1 dot V1 is 1. So, what do we have? Alpha 1 is equal to B dot V1. Therefore, what is alpha 2? Simple, straightforward, B dot V2 etc. What is alpha n? B dot Vn. So, what are we going to have? the basis expansion for a vector in terms of, let us say, basis expansion of B in a vector space V in terms of an orthonormal basis of V is given by B is equal to B dot V 1 in the direction of V 1 plus B dot V 2 in the direction of V 2 plus etcetera plus B dot V n in the direction of V n. Oh, this is not something new, we have seen this. For example, let us take R 2. In R 2, let us say I have my V 1 to be this 1 0 vector and V 2 basically the 0 1 vector. We know that V 1 dot V 2 is 0, V 1 dot V 1 is equal to V 2 dot V 2 which is equal to 1. Now, I want to express this vector, let us say 3 4 as alpha 1 into 1 0 plus alpha 2 into 0 1. This was nothing but 3 into 1 0 plus 4 into 0 1. How did we get this? This is nothing but 3 4 dot product with 1 0 in the direction of 1 0 plus 3 4 dot product with 0 1 in the direction of 0 1. So, what do we get? 3 into 1 plus 4 into 0. So, you get 3 into 1 0 plus 3 4 3 into 0 plus 4 into 1 into 0 1, which is going to be 4 into 0 1, that is what we get. So, this is basically the advantage of having orthonormal basis. If you have orthonormal basis, then the expansion of any vector in terms of this orthonormal basis is pretty easy. All you need to do is, given that vector B, you take the dot product with each and every vector in the orthonormal basis. So, whatever the scalar that you get B dot V 1, that is going to be the coefficient for the corresponding vector alpha, say if it is V 1. So, alpha 1 is going to be just B dot V 1, but the thing is all the vectors must measure unit length, the vectors, that is why it is called orthonormal basis, that means the length must be 1 in all these cases. Now, it is not something which we have not seen this before. The one that we have here where V 1, V 2, V n are all orthonormal basis, it is not something which we have not seen before. We have seen this elsewhere also. This expression whatever we have, let me rewrite this, let V 1, V 2 etcetera V n be an orthonormal basis, what we know what it means, V I dot V j is 0 if I is not j, and then V I dot V j is equal to 1 if I is equal to j, and let B be any vector in the vector space V with, okay, let us just make this small change here. Let V 1, V 2, V n be an orthonormal basis for a vector space V and let B be any vector in the vector space V. So, what I will go to do? I am going to write this B is equal to B dot V 1 in the direction of V 1 plus B dot V 2 in the direction of V 2 plus etcetera plus B dot V n in the direction of V n, right. This is going to be the basis expansion, is the basis expansion for B, orthonormal basis expansion for B. this is exactly what you would see when you want to express a periodic signal, some periodic function or a periodic signal which you would have seen, especially the guys from electrical, electronics engineering, electronics and communication engineering and all who and telecom engineering, who would have done Fourier series. Fourier series, when you do, I have a periodic function, I want to express this periodic function in terms of sines and cosines. So what do? I want to express this, let us say, as a naught plus sigma a n cos n x, something like this, plus sigma b n sin n x. Basically you want to have some periodic function to say, let us say f of x, something like this. We have a periodic, we call this as a periodic function. How did we get this a n? A n we got it very easily, you just took an integral, then you said f of x cos n x, of course you divided by the period, right. We had you had to integrate this, you divided by the period, you had all that stuff that you did. Ultimately what we did was, if you want to get the coefficient of the, let us say, cos 5x term, you took that function f of x, multiplied with that cos 5x and then did an integration. That is exactly what we do here. There your cos sign becomes the basis for an infinite dimensional vector space and orthonormal basis for the infinite dimensional vector space. Here we are talking about finite dimensional vector space. So we have finite number of vectors. So this, whatever in terms of our orthonormal basis expansion that we do, this is what we call as the Fourier expansion. You can go back and check how you got the coefficients for the Fourier series, you will see exactly this. So this is basically what we call as the Fourier expansion. Whenever you try to expand, do a basis expansion of a vector in a vector space in terms of orthonormal basis, we get into what is known as the Fourier expansion, right. So this is pretty interesting. Now what are we going to do from here, where are we going to go from here? Okay, we have expressed in terms of this Fourier basis, we have expressed in terms of orthonormal basis and so on. In fact you could even look at one more stuff here. What is that? We want to I want to look at the magnitude of b squared. So basically I end up writing this. This is nothing but b dot b, right. This is basically the dot product of b with itself. So I am going to have b dot v1 dot product with into v1 dot product with b dot v1 into v1. Similarly b dot v2 into v2 dot product with b dot v2 into v2. So you are going to have component wise stuff like this. What we are going to see is, this is going to be, let us say, b dot v1 the whole square plus b dot v2 the whole square plus etc plus b dot vn the whole square, which is again your Pythagoras theorem that you would see. And in terms of your Fourier, this you would have seen as your Parseval's identity or Parseval's theorem, right. Basically Parseval's theorem is Pythagoras theorem again, Parseval's theorem that you have, right. So this is something which you would see. Now where are we going from here? Having studied all these things, the next topic that we are going to study would be orthogonal projections. Why are we studying orthogonal projections? Orthogonal projections, what are the properties of projections? Projection as a transformation, we want to look at that, and once we look at projections, we will look at the idea of generating. So projections will then we will look at generating orthogonal vectors from linearly independent set of vectors, which is Gram-Schmidt procedure. Orthogonal vectors, we will look at this, followed by a very interesting thing. Basically this is using the Gram-Schmidt normalization process, and then what we will do is we will look at the QR decomposition here, The moment we get into QR decomposition, we will again go back to linear transformations which preserve length. We will look at linear transformations preserving length. And then what we will do is we will go ahead with the idea of real symmetric matrices. So, in this lecture what we saw was we were looking at the idea of orthonormal basis, how it is very easy to compute the coefficients, or when it is easy to express a given vector in a vector space in terms of orthonormal basis. And we also saw that orthonormal basis expansion is basically the Fourier expansion you have, and we related it to the Parseval's identity that we would have studied. And in the next class what we will do is we are going to look at orthogonal projections. What is it to say projection, and then how are we going to generate orthogonal vectors, which would actually be I mean we will study from the projections perspective basically the algorithm which is called the Gram-Schmidt orthonormalization procedure, and from there we get into another matrix decomposition called the QR, and we will study interesting properties of Q there, which is basically where we get into the idea of linear transformations which preserve length and so on. And from there we go to the real symmetric matrices which have certain very beautiful properties which are typically exploited in machine learning, especially when you talk about the variance covariance matrices and so on. So, that will be the focus of the next couple of classes. Thank you.